A seasoned mini golfer is trying to make par on a tricky hole number 5. The golfer must complete the hole by getting the ball from the flat section it begins on, down there, up a 47.5 degree ramp over a gap and into the hole, which is 2.35 meters away from the end of the ramp. If the opening of the hole and top of the ball are the same height, at 0.96 meters, at what speed must the ball V1 must be moving as it approaches the ramp to land directly in the hole? Soon the ball rolls without slipping on all surfaces. That's a good point to take note of. Once the ball launches off the incline, its angular speed remains constant. The acceleration due to gravity is 9.81. Okay, so I'm going to break this into 2 parts. So the first part is where the ball is rolling up the hill, and then once it reaches the top of the hill, it's going to fly parabolically, projectile motion into the cup. So what we want to do is I'm going to find the speed that it needs from this point and at this angle to make it just into the cup. And from there then, I'm going to backtrack to find out how fast it has to be going at the bottom to have this amount of speed at the top. And one of the things is, as it's rolling up the hill, it's going to have both a rotational speed and a linear speed. So we're going to have to take that into account as well. Okay, so first part, find the speed. This point here, I'm going to call this V top because it's going to be V, velocity at the top of the hill. And we need to find this. That velocity is going to need to get in that hole. So we're going to break this into 2 parts, and it's going to be projectile motion, or kinematic equations. So for the kinematic equations, first thing I usually do is I write up my kinematic equations. So I'm going to assume acceleration equals a constant. That's why I just wrote that. I can probably leave that off. There we go. Velocity equals at plus v naught, and x equals 1/2 at squared plus v naught t plus x naught. And the idea here is if you have a constant acceleration, you can take the integral with respect to time and derive the second 2 equations. And there's a couple of different ways of arranging these, but I like it like this. So first thing we're going to do is we're going to look at the, I'm going to look at first in the y direction, how long it takes for the ball to be in the air. So I'm going to use this equation right here. And even though I wrote it in terms of x, I can look at it in terms of any dimension I want. X is just kind of a placeholder. So I'm going to say that y final, which is this value right here, its final y position, it's going to be the same as its initial y position, that over there, and that's going to be 0. So it's going to start at 1 point, land at 1 point. We can choose any initial condition we want for that. We could do the 0.96, in which case this would subtract from that and you'd still get 0. Idea is they both cancel out. It's the change in height that you really need to pay attention to. So acceleration equals negative 9.81. I'm going to assume that down is a negative direction. And initial velocity, I'm going to do initial velocity in the y direction, is going to be v top times sine of theta. And so I'm just going to use the part of the triangle that's in the vertical direction. Okay, and then t, that's just going to be our mystery time. Okay, so now we do, I'm going to write this out. So we have 0 equals, I'm going to call this negative 4 point, no, because we want to use 9.81. So I'll just do 9.81 over 2 negative times t squared plus v naught in the y direction, v top times sine of theta times t plus 0 equals 0. The 0 on the right here, I can pretty much just ignore it because it's 0. We'll divide both sides by t. So this is given us 2 times when it's at 0. 1 time is when time t equals 0, basically when it starts, and that's not the one we're interested in. So we lose a solution, but we kind of knew what that solution was and we're not interested. So now we can say that v top, which is what we're looking for, equals 9.81 over 2 t divided by sine of theta. So what I did was I moved this to the other side to make it positive. and then divided both sides by sine of theta, and I was left with velocity at the top. Okay, and this is the data we get from the y dimension. Now we're going to do the same thing, but in the x direction. So we know that the ball is going to land in the hole at the same time in both the y direction and the x direction. I know that sounds kind of obvious and trivial, and maybe it is, but most things are obvious and trivial when you understand them. Okay, so we're going to use this equation right here. I'm going to say that x final is, I think it's like 2.35. That's the distance, 2.35 meters. X initial, I'm going to say, is 0. T, we know that. It's from down there. Oh, just draw a little arrow. Oh, no, we don't know what T is. That's still a question mark. I'll leave it as a question mark. V initial in the x direction is going to be V top times cosine of theta. Let's see, so we have T, we have V naught, we have a T squared, and A equals 0. Okay, so x final equals, going to get rid of the acceleration portion because that's 0 acceleration in the x direction. So the final distance is V top times cosine of theta. Yep, I'm pretty good with that. And so, times T. So I'm going to plug in V top. That's okay. We'll end up backtracking to find out what velocity of the top is. So we have 2.35 is velocity at the top, which we know is 9.81 over 2 times T over sine of theta times cosine of theta. So we have V top, which is 9.81 over 2 divided by sine of theta times T. And then we're going to have an extra T right there. Make sure we have two T's. There's a T in there. There's a T there. Yep. So there's a couple T's involved. So now, solving this for T, we're going to do T squared equals 2 times 2.35 over 9.81. And I'm going to call this tangent of theta, because sine over cosine. And therefore, T equals, go to the calculator, up, on, clear, make sure our mode is degrees, and we know theta is 47.5, 47.5, yep. Theta equals 47.5, oh, that was terrible, 5 degrees. Okay, so now, back to the calculator, second quit, 2 times 2.35 divided by 9.81 times tangent of 47.5, and this should give us T squared. Then we square root this, second answer. We have 0.723 seconds. Since it's less than 1, we square root it actually got bigger, so that makes sense. So now we want to find V top, and I'm going to use this equation up here. So the velocity at the top is going to be 2.35, which is x final, divided by cosine of 47.5 degrees, divided by 0.723, which is in seconds. So we have that number right there. And so we're going to do that number times cosine 47.5. That gives us the denominator. So we'll do 2.35 divided by second answer. Now we get 4.81. So the velocity, or the speed is a better way of phrasing it, because velocity has a direction, is 4.81 meters per second. All right, so that is our first point of data that we have up here. So the V top equals 4.81 meters per second. Okay, so now we're going to do the second part of the problem, which is we now have an energy balance equation. So I'm going to say that energy kinetic initial, actually, do they use an I there or 1. I'm going to use 0. Yep, I'm going to use 0 and final. So plus energy potential initial equals energy kinetic final plus energy potential final. So the idea here is this is how much energy it has at the bottom. This is how much energy it has at the top. And they're going to be equal because there's no, we don't have any energy loss due to friction because it rolls without slipping. It means no energy loss due to friction. And yes, I think that's good. So we're just going to have an energy transfer from potential to kinetic. Okay, so from here then, we're going to break up this energy. So energy kinetic initially is going to be, let's see here. We're going to have energy kinetic, I'm going to call this linear, plus energy kinetic rotational equals, and then energy potential initial will be 0 because we're going to assume it starts on the ground. And this is going to be, these will both be initial. Then we'll have energy kinetic linear final, just L for linear, plus energy kinetic rotational, you could use an A for angular if you wanted, final, plus its energy potential due to its height, which is going to be mgh. Okay? So then we can expand this again. You don't have to change colors every time. This is going to be 1/2 mv initial squared. Rotational, it's going to be 1/2 I omega squared. This is the moment of inertia. And I think we're talking about a ball here, which I'm going to assume is a sphere. And this is how its angular velocity. And this is going to be both initial. Then we're going to have 1/2 mv final squared plus 1/2 I omega final squared plus mgh. And so what we're looking for is this value right there. Let's see here. Assume that the ball rolls. Blah, blah, blah. So if the opening, at what speed V1 must be moving as it approaches the ramp. Okay, so we're going to find its initial linear speed. So first thing we need to do is we need to convert this into something that's a common unit here, because there's a relationship between angular and rotational. So the relationship, and I usually start this with x equals r theta, v equals r omega, and acceleration equals r alpha. The reason I start with this top one here is because this one you kind of know in your head. A distance around a circle is going to be 2 pi r, because it's the circumference of a circle. And if you look at it in terms of angular, the distance and angles around a circle is 2 pi, and r is r, so you get the same answer on the left and the right. It's just kind of a mnemonic to help memorize this, the relationship. And this relationship only holds true because there is no slipping. Okay, so then we can do the same pattern with velocity and acceleration. We have r times angular acceleration and a for angular speed. So the one we're going to be concerned with here is omega, where omega equals v over r. Therefore, omega squared equals v squared over r squared. And now we go on and look at the moment of inertia. And this is something you can, there's just some certain shapes you know in life. You can also look them up. Wikipedia has a good list of moments of inertia. For a sphere, moment of inertia sphere, this is due based, I think completely on geometry, just the geometry of the shape, is going to be 2/5 mr squared. So what we're going to do here then is we are going to now rewrite this. So this is going to be 1/2 mv initial squared plus 1/2. Now I is going to be 2/5 mr squared times omega squared, which is v squared r squared. V squared r squared. And then it's going to have the same thing for the right side. I'm going to copy and drag this a little bit. Yep, I'm going to stick with blue. So we have 1/2 mv final squared plus 1/2 times 2/5, which I will reduce shortly, mr squared v final squared plus mgh. Okay, so we know a v final squared. V final squared is going to be v top. Oh, gonna do some canceling right there. So now we have, and then we get the r squareds cancel. V final squared over r squared. Yep. And so let's see here. So we have 1/2 plus 1/5. So I do a little sidebar here. Plus 1/5. The common denominator will be 10. So 5 over 5, 2 over 2. This is the same as 5/10 plus 2/10, which is 7/10. Okay, so we have 7/10 times mass times v initial squared equals 7/10 mv final squared plus mgh. Everything has a mass involved, which means the mass doesn't really matter. And therefore, we can say v initial squared is 10/7. Oh, that looks like a 16, which is going to create confusion, times 7 over 10 v final squared plus gh, which, so take a look over here, and we had 4.81. Seems reasonable enough, plausible, maybe. We'll go with that. So plug that into our equation right here. Take 4.81. We square that times 7 divided by 10 times 7 divided by 10. Yep. Plus 9.81 times 0.96, because 0.96 was the height, times 10 divided by 7. And then we take the second square root, second answer, and I get 6.049. 6.049 meters per second. So that is how fast I think it would have to go. So the idea here would then be, if you hit the ball, it has some sort of angular and linear speed. It has that little angular and linear speed coming up, and then it has to do a projectile motion to get in that hole. First thing we did was we broke it up into two problems. So we found the projectile motion problem, and we did it as conservation of energy. And we did conservation of energy, we had to take into account rotational energy as well as linear. So I did all this math, and the final answer was 6.049 meters per second. So hope that helped. See you next time.